all about serial communications. Let me open. I have some material from another course. I have the digital sensor interfaces. I'm actually also teaching the what is that called? Interfacing sensors course in Metropolia. I have actually a couple of times also offered it for Frankfurt students, but not this year, not next year. The following year, you may be. But anyways, so basically it's all about sensor interfaces. And when we are talking about sensor interfaces, all of those are nowadays, they are basically serial line connections. And on serial lines, basically you can have either asynchronous and synchronous serial data. The only difference between those is that if it's a asynchronous signal, it means that it has a it doesn't have the clock line. The synchronous serial communications have also the serial clock for data transmission. So any other, if there is no clock signal, then it's asynchronous, and the synchronization is done on both ends, both the transmitter and receiver end. Okay, that's just one definition, what is sync and what is async. Today's beef, first beef is right here. It's about the serial communication between your black box, which is your PSOC board, and PC. I have a feeling that these maybe those desktop computers may actually have the real serial port, the 9-pin D connector there. There might be still, but this is kind of vanishing type of connector because it's big and bulky, and it pays about €2 instead of 2 cents. Okay, but anyways, the protocol is not going anywhere. Protocol is not going anywhere, and for that one, actually, there is also these nice small gadgets that can be used for plugging a serial communication to computer using virtual COM port. But I have a slide for that one later. On PSOC circuit, actually, there are several different serial communication blocks there to choose from. Most often, it's the universal asynchronous receive transmit circuit what you are using, or some variant of it. There's only one exception, and that's actually the SPI. SPI is a synchronous data transmission line. Okay, but anyways, that you probably have played with that word in some other course. That's the most common way of starting a communication between devices. Simple serial line connection. You just set the bit rate, parity, stop bits, and start transmitting. That's the normal way of doing a wired transmission. And in addition to the UART in PSOC, there's also the receive and transmit modules, which are used on all sorts of the data transmission. Okay, so basically, well, we'll go through that later on the demonstration part. But anyways, when we are talking about serial line, that's the most common. Used to be most common, and that's the vanishing kind of serial port, the D9 connector on the PSOC board, and maybe if you have old enough computer, you can find the same from your computer. But if you find a D9 connector from your computer, you might consider buying a new one. Okay, so, but anyways, that's the traditional serial port communication. Data signals are transmit and receive. So basically this is full duplex, meaning that there are separate lines for transmitting and receiving. And then of course you need ground. In addition to that, there are also handshaking signals which are commonly not used. Usually the OART is capable of transmitting and receiving with buffer, meaning the handshaking is not necessarily needed anymore. The computers and even small microprocessors are fast enough to get all the data out of the device before the next one comes there. But anyways, those signals are standard signals, and those are mentioned here. Data terminal ready, data set ready, and so on. And actually, the last one here tells more about the history of the this RS-232 ring indicator. Okay, that is basically the standard communication channel for the area of modems. So standard telephone line, and there you have this modem to connect the data to the line, and another modem on the other end, and one end is thus calling to other end, and there is special line ring indicator which then basically sets the interrupt on one end, and well, magic happens. Okay, voltage levels on original RS-232 line are actually, they are inverted and funny. So -15 to -3 volts is logical 1 or idle signal, and then +3 to +15 volts is logical 0. So anything between those. And basically the signal -3 to +3 volts is reserved for the error margin. So nothing happens in between those signals. Of course, there are some receivers and transmitters later on which were designed so that you can actually send single-ended signals, meaning just positive 0 to 5 volt signal level. Some receiver and transmitter circuits are capable of handling those, but that's not part of the standard. This original 0 port uses D connector. If it's a male connector, then it's data terminal equipment, and female is data circuit ending equipment, meaning basically a modem type or the equipment, the terminal type. Okay. So this looks like it's modem type, which means that you can directly plug this one into the terminal type, although it doesn't fit anywhere, since this is too deep down here. But anyways, it's old standard. And then about the parameters of those, the most common parameters, at least few years back, were still the 9,600 bits per second transmission, warping speed, 8 bits, no parity, 1 stop bit. So that's used to be the most common. But well, these computers are capable of handling much higher data transmission speeds, and if you are not using the physical the RS-232 but a virtual one, then you might actually consider cranking the speed up much higher. Okay, but anyways, that's part of history. When I was young, when your parents were young. All right. But anyways, the connecting physical devices is very easy. You just take the wires and basically cross them between two data terminal equipment devices. And then provide a common ground. One small thing, of course, because it's asynchronous, you have to agree on what is the bit rate and other parameters. So both ends must know the transmission parameters. There's no other way of knowing how to actually detect the transfer rate. There are some hardware actually that, and also you can find it out by software, but that's always non-standard kind of thing. You can, for example, think that okay, the other end is probably sending character 13 or 10 or both of those carriage return line feeds, meaning you are hitting the enter, and then you change the baud rate until you start getting those characters. That used to be the method the terminals to talk with their mainframe computers back in good old days, which were not good. They were just old. Okay, but this is the more modern kind of way. So modern PCs don't have real RS-232 boards anymore, thank God. But basically, there's a virtual COM port. Virtual COM port basically means that you have a USB device, and on USB, one of those the standard devices on USB is the virtual COM port device. So basically, when you connect, for example, the programmer pod part of PSOC 5 board, that works as the virtual serial port. So you can then just wire your the port device of PSOC 1 here on certain pins, and then you basically can start transferring data using virtual COM port. Okay, yeah, don't snap it off from the board unless you have a good reason for it. I just found this one from the box. It doesn't hurt if you just have it attached. Okay, back to the beef. So basically, the previous one was about sending data to PC or receiving commands from PC. The more interesting part is the data communication between digital sensors and this nice black box. Okay, so some serial buses. Usually if a sensor has a serial bus, it's designed so that you can actually attach multiple sensors into one single microcontroller. For example, in cars, you cannot buy a car without CAN bus anymore. That's more or less industry standard. Or some CAN variant, they just call it differently. Yeah, and of course, the Italian ones, which don't work. I know, I have Italian motorbike. Okay, so, yeah. So that's why you cannot even replace a light bulb anymore. You have to program it to the car computer to recognize, oh, now there is a new light bulb. Yeah. Something was better, in good old days. But not cars. Cars are much nicer now. Okay, but anyways, so you have one single the microcontroller, and you get data from several sensors, and as little as possible cabling. That's the biggest thing. You really have to cut the amount of wires in any equipment. Cars, they have more than 10 kilometers of wires. Okay, more than 10 kilometers. CAN bus actually has more or less half the amount of wires needed in cars. So it used to be 20 kilometers. Now it's only 10 kilometers. Okay. So that's one serial bus, one wire, misleading name. Of course, there must be the common ground. Otherwise, it doesn't work. But anyway, the signal needs only one wire to connect, and not just the signal. The most of these one-wire devices are also capable of running on the parasitic power on the line, meaning it just needs usually a one capacitor as the current bank or the charge bank, and then it just needs one single wire to operate, of course, with the ground wire. So yeah, that's as little as you can go with the wired connections. All right. Okay, so this actually has the transmit and receive signals on the same wire, which means that, of course, one device can be only present at or sending data at time, so it means that it has some protocol issues. As soon as you put more than one component, one sensor, you first must go through the device discovery before you can access those sensors. Okay. And okay. Because of the charging properties, there is a downside low data rate. 16 kilobits per second is considered very low data rate nowadays. But yeah, nice thing is that you can actually have lots of devices there. One wire devices have unique 64-bit addresses. 64 bits. Okay, so that's enough for, let's see, 2 to the power 64. How many devices you can put on the Earth with that amount of bits? I think it's something like 1 per square meter, including all the waters. Not enough. Okay. No, it's not. It's more, right? Someone should calculate, 2 to the power 64, it has a lot of zeros on it. That has, let's see, 2 to the power 10 has 3 zeros, and then, this much. Yeah, so, and then divided by the how many square meters there are in, let's see, what is the Earth's, how many square meters there are in Earth, and divide by that number. And no, the other way around. Divide that number by the square meters per Earth. Okay, that's a lot. But anyways, so I guess we have enough of addresses for the temperature sensors. Okay, that's how the parasitic power thing actually works. So on those devices, you usually have a simple rectifier and capacitor. Well, the capacitor actually, I have seen that usually that's that's actually external. But anyways, for example, that one wire temperature sensor we are using, it can be run also on the parasitic power. But as long as we have real power, well, why not to use it? Okay, PSOC. Yes. There is a PSOC one-wire module, and that's how you connect it. You basically have one-wire bus by connecting two pins together. So you have a one-wire user module, and you actually have to connect the physically input and output together. You cannot connect it inside of the device. It's not supporting it. So basically, and then you have this one pull-up resistor there, and then you can connect it, for example, that 18S20, this 18S20, the one-wire temperature sensor. Good. There we go. Some applications. Well, you can find more of those from internet. But anyways, one what we will be using. Oh wow, broken link. Sorry about that. So DS18S20. Maybe I should actually. Okay, datasheet. I should use that one. Okay, but yeah, so that's what it looks like. We have this 3-pin version. Again, be careful when you are connecting it. It might actually burn if you reverse the polarity. Might not, but don't mess with it. Don't try your luck. Read the manual. Okay, so yeah, so basically down somewhere in here, actually, we have some description of the memory location, and okay, it has internal registers that you need to read using one-wire protocol. But nothing to worry about, since there actually is the some sample, not code, but a sample how to do commands here. Operation example. So, okay, maybe that other one. Only one device is connected, and basically this is what you would be doing first. First is your reset, and then basically to check the presence, meaning that you just take a look at the register from your one-wire module. Was there something online? The next one will be issuing some commands and waiting for response. Yeah, so that's basically the protocol how to do it. If you feel like, you know, finding some almost working examples on internet, I don't care. You can do it. I'm sure that somebody has already tried that one. Not necessarily it's on piece of one board, but also, well, Arduino. I hate Arduino. Arduino is a toy. It's not used anywhere else except education and toys. You'll be working probably also for German car makers. If I ever buy a German car, I would like to have their not toy parts, but real parts. Okay, just a reminder that in Finland, the last winter on January, we had minus 30 degrees, even in Helsinki. Toys don't work there anymore. Okay, yeah. So, but anyways, so that device you will be learning how to read the temperature. It's not that hard actually. You just follow this protocol. What has to be done? Just writing bytes and reading bytes. And how to get the data basically when you read the scratch pad. Okay, you will be actually reading 9 bytes out of the scratch pad. And of course, if you're looking at the scratch pad, let's see, where was it? Okay, the temperatures are actually the first 2 bytes, and then the last byte what you are reading has the cyclic redundance check. So without reading all the 9 bytes, you don't know if the data is valid or not. Okay, good. Back to the business. So yeah, lots of one-wire devices available. Okay, another this integrated circuit kind of buses is I2C, which is IIC bus, so integrated circuits, meaning between 2 integrated circuits. Originally developed by Philips, but of course, because it's registered trademark, some people thought about in Maxim and other companies, let's call our version 2-wire, but it does exactly the same thing. So it's hacked protocol. 2-wire interface, they call it 2-wire, and they don't need to they don't need to pay to Philips. Life is not fair. Yeah, I know. It's synchronous bus, meaning there is also a clock signal. That one wire is async, internal the synchronization, but I2C has actually clock. Both clock and data line actually are kind of open collector drive with pull-up resistors. So practically, this can be a single master, multiple slave, or multiple master, multiple slave bus, as long as the protocol is somehow managed between the multiple master. Okay, there are actually, it says each device has 7-bit address. Yes, and in addition to that, there are also 11-bit addresses. Okay, now we have much less addresses as on the one wire. But anyways, that's enough in any case, since you don't usually need more than tens of devices in one bus, especially when you think of this kind of bus which has the its asymmetric line, meaning strong 0 and weak 1 state. Okay, think of longer wires. You're starting to get a lot of capacitance there too, and which means that it's at some point you cannot extend the bus anymore. In any case, okay. Yep. Communication looks like that. So basically, serial clock and serial data, sorry about those, actually the SCL and SDA are a little bit too low. The upper is of course the serial clock, and serial data line is the lower one. And when data line goes down before the clock line, that's the start sequence. Then all the devices which are on this I2C bus actually are listening. Okay, what is the address? So next, the this master sets the address byte. 7 bits plus, is this a read or write operation? If it's a write, then basically the next byte will be command byte. If it's a read, then it expects a device to respond with data. Okay. And then the stop is opposite to start. So the clock line goes high and then stop goes, data goes high. When sending data, basically, let's see, does it show it? No, it doesn't show it totally correctly. So basically, these data lines cannot change when the clock line is high. Yes. So to prevent the accidental stop sequence at the middle of data. Okay. So yeah. So that's the protocol. And I always forget this acknowledgement bit. So when you are writing an address and there is a device, then this acknowledgement bit is actually given by the device. When you are reading data, then basically the master should put the acknowledgement there. Okay, data received. But fortunately, the PSOC module does all that for you. You just need to check what kind of things come back. One thing, of course, is you need to check by software that if there was an acknowledgement bit given. Otherwise, you don't have a working device. Okay. What is that one? Transmit and receive. So yes, you can actually have this sequence where you first have the address, you write the address, and then you write the command byte, and then you repeat the start and continue with the reading. Okay. For example, I think this I2C devices usually, for example, the I2C memories, you first write the address for the memory pointer on the I2C EEPROM, and then you start reading from that forward, one page at a time. And that's done so that you have first the address byte, command byte, and then repeat the start and continue with the read sections. Well, yeah, meaning that again the same address but with the read bit, and yeah, that's how it goes. Some I2C devices TC74. I think that's our choice for the. Let's see. Yes, that's our choice for I2C bus device. I have the TC74A2-5.0 VAT. Yep, 5 pins device looks like that one. It's simple. But it's like that. These devices are usually connected to some, say, for example, on power electronics to check the temperature of that the heat exchanger. That's why it's on this kind of can. Okay, and then some other examples on I2C. And I already told you about the I2C EEPROM is quite familiar, quite often used in embedded systems as the non-volatile memory. Yeah, I'm not going to that one. Okay, I2C is used not only on this kind of sensors, but for example, on the batteries, smart batteries. Okay, that's how you make sure that nobody changes the batteries themselves. They have to buy the service from a shop, since you need to. There's a serial number which is checked, then you need to do some flashing to get the system acknowledge that new battery. Okay, that's how you get people to buy services. So SM bus, meaning system management bus, is used, I think HP is using and Dell is using those in the smart batteries. Okay, and yes, PSOC has I2C, the master, 3 different versions. When you look at this communication protocol, that ain't that bad actually. You need 2 pins. Clock pin is actually just one LED device, which is software device. The other pin actually should be able to both read and write. So you put a control to a pin that it turns it on 3-state, high Z 3-state on some ports. Actually, no, you basically make it, so pull down. No, open collector. Yeah, open collector kind of. So with a strong 0 and weak 1. Then you can actually release the line. So it's very simple to also make this protocol with software. So any microcontroller can do it. So that's actually why on these PSOC circuits, there's a software I2C master module available. Okay, it just takes some software. It doesn't need any digital blocks. Then basically it just needs 2 I/O pins that you can freely select. Then there's the hardware implementation. I2C is also the favorite choice for flashing stuff. So basically this connector here connects to the hardware I2C bus of the chip. When you set the reset bin, then this device actually transforms into I2C memory. And this programmer is just pushing the data to the I2C memory here. The flashing is done that way. No brainer. That's why these are something like €1 each. Okay. And that actually comes with the fact that only 2 options for I/O pins. So it's either this programming pins here, or there's also another 2 pins that can be used as I2C pins for hardware I2C pins. Then there's easy I2C, which is the hardware implementation, but this is slave only, meaning that if you need to use this device as I2C something. For example, yesterday you made this data acquisition system with easy I2C slave. You can transform this one into data acquisition system subsystem for some other processor. Have you been using Raspberry? Raspberry does not have A to D converter. but it has I2C bus. So if you need a real A to D converter, then that's one option. Just plug a PSOC circuit next to the Raspberry and write some code. Not bad. Okay. Yeah. And then some details about how to do the selections for these modules. Okay, next one. So we had one wire, then we have this I2C. The next one is SPI. One wire is slow, but there's plenty of devices and it only takes that one single data wire. I2C requires two, and it still has some limitations on the bus length because of the capacitance of the wires and the weak pull-up resistor kind of the weak one state. Okay, SPI, it's different. You basically have the strong line drivers, and you can actually even extend the lines with the having these balanced data transmission lines. So SPI can be very, very fast. So fast that it can be used, for example, as the data line for the data memory modules, flash modules. For example, this extra memory for your mobile phone. When you plug in that small device there, it has SPI on. That's why it's actually pretty fast. And also, say digital cameras and that kind of interface, they usually have the SPI bus. Okay, but the other side is that well, it requires 4 wires. It has the serial clock, which is driven always with by SPI master. Then you have these 2 lines for data. One is master out, slave in, MOSI, and master in, slave out, MISO, depending on which way the data is going. A to D converters, for example, they don't have the MOSI line at all. They have the MISO line. And then it has slave select. So low active signal that puts each of the devices on or off. So basically, you can have common line for clock, MOSI, and MISO, but each device must have their own individual the chip select line, unless they are actually devices that can be cascaded. So then basically you will be cascading the both MISO and MOSI too. But well, that depends on the chip manufacturer. This 10 megabits per second is kind of speed that can be easily achieved within one circuit board. But okay, with some extra electronics, that it can be even higher than that. And as I said about the cabling with multiple devices, you can have these the slaves on the same clock, MOSI and MISO, but then both must have separate slave select signals. All right. And that's about everything that is in the standard. what is not in the standard is when the data is set, valid. High active clock, low active clock, clock inverted or not. That depends on the manufacturer. So most common, I think, was mode 1. Or was it mode 0 and 2? No, non-inverting clocks and leading edge. Yeah, I think it was in mode 0. And mode 2, and some devices actually can use both at the same time. But that's something you need to check from the data sheet of the device manufacturer. All right. So one real life example. This was basically by the way, this is my former colleague Juho Vesanen did a really good, nice job on this presentation. I'm just showing it, but this is a real data transaction between a microcontroller and a device. So, okay, serial out, serial in, clock. Seems that in this case we have clock is inverted. We have chip select low active, and then we have serial in and serial out, so that serial in is the MOSI and the serial out is MISO. So chip select low and bits are locked on the rising edge on inverted signal. Okay, inverted clock rate, and that's where the data is sent, and it's the most significant bit first. Okay, and of course there are the depending on the device if it's a more significant bit first or the least significant bit first. But well, that's something you need to check from the data sheet. Most significant bit first is the most common way on any synchronous line. All right, and then yeah, and the same thing from the 1 byte from microcontroller, 1 byte to microcontroller. So there's the chip select, and then we have the read and write bytes there. So first one is writing the data to device, and the second one is reading from it. There. All right. Some comparison, since we have the SPI and I2C. Okay, that's basically partly true. So I2C is for low speed, long-ish range. It still has the the capacitance of the line is defining the highest or the longest line you can actually have. But anyways, both I2C and SPI can be found in most handheld devices. So your mobile phone probably have both of those buses. SPI for the flash memories, audio codecs, but I2C for some other stuff, and of course one wire too. I would guess some of the devices will be on one wire. Sample devices. There's TC74 actually has dual the wiring. It can be either I2C or SPI. In our case, the SPI device is actually MCP3201, which is a 12-bit A to D converter. Okay. So that governs devices in SPI. And yes, SD memory cards has SPI bus. Some other devices that can be usually found with the SPI. They are really nice small radio transmitter or transceiver devices like the NRF24. So that's 2.4 gigahertz data transmission, and it's say fairly popular on all sorts of applications. Fits in lots of purposes. And then, yeah, say Bluetooth low energy modules you can find with the SPI. And Ethernet. It's fast enough, but for Ethernet. With I2C, it's not fast enough actually to get data in and out for full speed Ethernet cable. So, but with SPI, that's easy. There we go. What else? Yes, PSOC. Okay, we have SPI slave and SPI master. Yeah. Just needs clock signal and then MISO and MOSI. All right. Yada yada blah 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 those stuff. That's all. That's all about those things. And next, what we could do is to take a look at the first the exercise. Okay, so yes, exercise. Let me close that one for a while since yesterday. Yesterday's memory. So yesterday you have at the end of that exercise you should have more or less this kind of system. A to D converter. Then you have the decimator, and that data goes to LCD. Today you basically go and make a copy of that one. So not starting from scratch, but if you got something working, you can basically just go and copy that one for the basis and add here the one wire temperature sensor. So this one gives actually that temperature 1, that one gives you temperature 2 with the one wire module on the PSOC, and then you have these two things, and you also have possibility to use the UART. There you have the TX and RX lines, some buffering maybe, or just the USB serial, the converter. Then you have USB line to computer. And send both T1 and TS. I think I will asking you to send with the JSON format. JSON, JavaScript, something. But anyways, that data is very simple. It's all strings. Basically, this would be one transaction C, and well, you can take a look at the JSON format from the internet to find out how to actually encapsulate that one. And this is just basically strings and how to test it. On PC, you would use some terminal program and see that that stuff actually appears here. Easy. All right. Then some hints how to do that. So yeah, we start from yesterday, and I'm actually marked. So this is new, one wire, and then that is new. Well, that part is basically new part. Okay. Let's see how all of this is done. Okay. So yes, you already have the following stuff. Just checking that I didn't tell funny things to you. Okay, I have the in here I'm actually telling about DS18B22 Plus, which is the latest model of that DS18B20. You actually have the DS1820. So take a look at which device you actually have and take that data sheet, preferably from the manufacturer page, which is our Dallas Maxim. DS stands for Dallas, but Maxim actually purchased the Dallas Semiconductor. So DS1820, but you might actually try to read what it says on that device itself, since this labeling might be also wrong. Okay, but anyways, so data sheet you can find yourself. And you already had the 2 samples per second downsampler for that LM35, which was connected to the display on LCD, and then that one-wire sensor to PSOC. There's application now note how to actually employ the one-wire. Use these ports 1.6 and 1.7, okay, which are sorted outside of the circuit. Okay. The device itself, it's slow. So if you try to sample it twice a second, it doesn't work. I think it takes about 800 milliseconds for the data to be ready. Okay, so while the oversampling, actually this LM35 is sampled twice a second. This is done only every other time. And yes, there is add a word. Actually, here you can also have just the wait a minute. Or actually, it's what the hell? Transmit. 8-bit transmit. Either full word or just 8-bit transmit. Let's see. No. Sorry. Yeah. So basically, the receive. Okay. Receive and transmit means that it's then full word. So I would guess it would be better to use just a full word. Then you don't have 2 different devices. But it depends how you allocate those, in which places you can put them. If you cannot put the full word there, then you can always put it. Or usually you can put the separate transmit and receive. All right. And then testing your communication channel. All right, that's one way. Use terminal program. Okay, now the question is what kind of terminal program you have on these computers. Yeah, MATLAB is there. Good. Then you need to open the serial line and start listening what comes back. Okay, and yeah, of course, the setting up the parameters. LabVIEW, yep. So have you played with the LabVIEW serial ports? That's the same thing. You just take the serial port block and, you know, do some software with the LabVIEW. My favorite is actually PuTTY. Okay, I'll show you. So, excellent. So that's the easiest way of having a terminal, general use terminal on a computer. All right, and their serial port and serial line is whatever is your serial line. Okay, how to find the serial line? If you have the real 9-pin serial port and only one of them, that will be COM1. If there are two, then one is COM1 and another one is COM2. But most probably you don't have any physical serial lines, which means that you will be using this translation block. Let's take a look where this one puts the serial port. For that, let's see. Now, where do I fit that one? Here. So when I put the this one in, it installs drivers, and then actually by using the device manager. Device manager. Okay, lots of network adapters. You can see ports, and okay, that's nice. This is called KitProg, and currently it's actually COM13. Okay, one say small caveat on these virtual COM ports is that every time you put a little bit different device, for example, just the serial number of that device is different from the other one, it will renumerate and give it a new number. So when I started a few years back with this computer, plugged my first of these KitProgs there, it gave me COM port 2. 2 years later, that's where I get my COM port now, COM13. Okay. Another thing about that, let's take a look at the parameters. Where did it go? Properties. Port settings. Okay, that tells you what are the current settings for this COM port. You can change this, but then you need to also change this on the other end. So practically plug in that the USB serial thingy, which is also a PSOC programmer actually. It works as the PSOC programmer for those PSOC 5 boards. And yes, it also could be used for the PSOC 1 board. But we have the different ones to use, so we will be using them. So, and then Markdown. Okay, what was the COM port? COM 13, and that's 9600. 8 node parity, 1 stop bit. Mark down the serial line parameters. And don't be surprised if you plug this one on different USB port. You will get different number. Okay, now you have been warned. So that's how you get the serial port access or virtual serial port access. After that, you can now actually take the where was my putty? Putty. All right, serial port COM 13 and 9600. Yeah. Open. And I'll show you how it actually works. On this device, actually have the lines are now open, so it's getting some extra stuff coming in. Yeah. When you're starting to get this kind of information, it means that you have just static noise on the line. But enough, since RS-232, when you get a rising edge on the data, it immediately starts the locally the synchronization. And okay, when it gets that one, it reads whatever bits there are on the line. Well, I have static noise on the line. Yeah. Okay, but it definitely it's a functioning device, so I'll just close that. Alrighty. So there you have the terminal connection, and in principle you should be able to get some data, not binary data. Make those strings first and then write them to the terminal. Did I ask the JSON format? That's my question actually. If not, I need to change it. Okay. Does it say anything about sending the data to the? Okay, I got it. Port sense content, low sample rate. Okay, I'm not requiring the JSON data. It's just a say string data. Yes. Otherwise, it's hard to actually interpret. Number 27. What is the character? It's character 27 is what is the? Let's see. It's nothing. Yeah. No. 27. No. Okay. I used to remember how to do it, but anyways, so the send string data. Otherwise, you're getting funny characters. Okay. So next, let's take a quick look at how to make the copy of yesterday's project. So when you are creating a project, you go to new project, but then actually where it is There, project creation, clone existing project. Click, clone from project. That was yesterday. There we go. Open and give it a new name. And there we go. We have a wherever I ended yesterday, I get it here, and I can start modifications. That's actually quite nice. On also a trick for the version control. When you have one part working, you make safe copy of it by continuing by first making the clone project and then continue, since it's it's not good idea to break something that works already. Okay. And by the way, are you familiar with GitHub? Okay, that's also another nice idea when you have these projects. But on the other hand, you should have started it already on Monday using the GitHub, right? I have found it pain in butt, trying to the middle. Okay, now I moved it to GitHub. All right. But anyways, so version control or nice way of continuing whatever you did. And okay, this is also the way if you need to change the processor. If you find there's not enough resources on this processor, you can go and pick another one with more devices, or other way around. You pick the biggest processor they have, but it's €2 something, and for the production you want to go to the cheapest version that can do the job. Then you basically would create the project for the cheaper processor. $199. Okay. I haven't tried that. No, I haven't used that. So that's the safe way, on the creation of the project. Start from the like cloning the old working one. Good. What else? Yeah. Then these blocks, what I used, or you will be using, this one-wire block, yeah, and datasheet. Okay. Wow. Well, that's why I have the transmit and receive different. I have only one digital block here to use. Then I2C master. Didn't take any blocks because it's software. Okay, I have one wire, I2C master, then SPI master. Wow, I'm out. I actually don't have any blocks left anymore. So I have to use the software transmit and okay, I see. I ended up in a small problem here. So basically, you might actually skip the one block here, the low pass filter from yesterday. Otherwise, you don't have enough of digital blocks to do this. Or use some other A to D converter as yesterday. Otherwise, you run out of digital blocks. See, all of these are used. No blocks left. and we still need to have the UART. And UART is requiring, I think, 2 blocks. Oh, I have PWM here. Oh, okay, good. Yeah, you're right. That I played around. Thank you. Okay, so you can do it. I couldn't do it anymore. But anyways, that's the a situation that you can actually quite easily to have to run out of the blocks. So there are options. You start rethinking of what kind of devices you will put there, or take another processor type. I like this 27443 processor because this is still readable. If I had more blocks, all those blocks get about half of the size and nobody can see them anymore with these displays. So for education purpose, this device is perfect. And also perfect in the sense that these resources, what you have, they are not unlimited. They're very limited resources. Okay. And yes, there is still one more way to add more devices would be to, let's see how to do it. You can always add a new loadable configuration. So basically, if you run out of blocks, oh, wait a minute, where is it? There. Basically, you can always have different software loadable configurations. So now that one releases all the blocks. Only the wiring remains the same. Okay. But anyways, shifting between these blocks would require a little bit more software. So I'm not recommending it unless necessary. Okay, so those were all the tricks I wanted to show you today. You need to figure out the rest. So one wire Y2C SP, okay, then I have the UART. Does it go anywhere? No, it didn't. Okay, maybe if I put them here, those here. Well, come on, nothing happens. Can I now add the UART here? No. Maybe I need to take that one first out and then put the UART in. Let's see where does it go. Now that one wire. You need to fiddle with the blocks. Okay, good luck. Yeah. Yes, let's see. Does it? Oops. Wait, one wire here, and then basically, oh, okay, now I got it. I can always use that RX8. That should go somewhere. Come on, there. Now actually I can have the software transmit. Okay, that's why I had the in there using software transmit and hardware receive instead of UART. Not enough blocks. By the way, Cypress actually recommends using the biggest processor to start the project. But, well, I'm doing this with the smaller processor for a reason. Good. Yeah, that's one way of putting stuff there. And then, of course, you need to configure everything and write tons of code. And now you probably have lots of questions. But anyways, I'll stop with the my recording now.